Hello everyone, welcome to this next video of CM1 from SMonk. So in this video we're going to develop our concepts of interest rates and discount rates that we have developed in the previous few videos. So here we're going to understand what is nominal rate of discount and nominal rate of interest and effective rate of discount and effective rate of interest. So let us first start with the interest rates. So let us see what is nominal and effective rate of interest. So let us start understanding with a very simple basic example. So for example, let me say the interest rate is 1% per month, rupees 100 invested for 1 year. What is the accumulated value? Simple question. So now by default everything is compound. Now whenever the question says simple, it is simple, otherwise by default it is compound. Nobody is going to ask you questions usually mostly on interest because it is not a widely used interest rate. In our organized sectors we only deal with compound. So sometimes the question may ask to deal with simple interest or simple discount, otherwise in most of the cases it is by default compound interest if nothing is mentioned. So here 1% per month refers to compound interest. So my solution is 100, 1 plus 0.01 raised to 12, 1 plus I raised to n. Here I wrote n is 12 because my time unit here is per month and I'm investing for 1 year. So there are 12 months in a year. So this becomes my answer. So here my answer comes out to be, let me check on the calculator, 100 into 1.01 raised to 12. The answer is 112.682503. So the person had invested at 1% per month and he kept his money invested for 1 full year. Now by the end of 1 year, how much returns have he actually earned? So we can check actual rate of return for 1 year. The person has earned 12.682503 rupees on an investment of 100 rupees in 1 year, which makes it 12.682503%. So the bank, if the bank pays annual rate 12.682503%, or if the bank offers 1% per month, both are actually the same thing. There is no difference. They may sound different to you, but they're actually the same thing. So there is no difference between saying 1% per month or 12.682503% per annum. But if I say 1% per month is 12% per annum, it is kind of a wrong representation of the fact. 1% per annum is not equal to 12% per annum. 1% per month is not equal to 12% per annum if it is compound rate. So interest rate is 1% per month. Interest rate is 12.682503% per annum. This is statement number 1. This is statement number 2. I'll write one more statement. So look at it very carefully what I'm writing. Nominal rate of interest is 12% per annum payable monthly. I've written 3 statements, 1% per month, 12.682503% per annum and 12% per annum. So 12% per annum is not actually the real rate. It is not the actual rate of return that is being paid. The actual rate of return is 12.682503. So with 12% per annum, we say that it is payable monthly and we use the word nominal. So this is just a way of writing an interest rate. The statement is not wrong. This is just another way of writing the first statement or the second statement. So all above 3 statements are exactly the same. All 3 have got the exactly same meaning. So let's understand it this way. That you are a banker and you're dealing with a layman consumer who do not understand compounding rates very well. So when you want to explain him that your interest rate is 1% per annum and his interest rate is 12.682503% per 1% per month and 12.682503% per annum, he'll not be able to understand how 1% converts to 12.6825% because he do not have the scientific calculators or he have not studied this concept to understand this very easily. So just a way of presenting or a standard way of writing, the banker would tell a consumer that your interest rate is 12% per annum but payable monthly, because 12% is a figure that clicks very easily to him. So the explanation that I'm giving is only for understanding. You can understand it this way, you can understand it in some other different way, but at the end what matters is that you understand how it is being written. So 12% per annum, payable monthly. 12% figure is what satisfies his mental calculations, and payable monthly makes him come to the conclusion that it is 1% per month. So it is actually a very good way of presenting. By the time the interest accumulates for 1 year, it is 12.6825. So he will virtually or he'll practically see that money growing. So he'll understand how this has grown to 12.6825. But even before the money grows, if you try to explain him how this converts, how 1% per month converts to 12.6825, he'll not be able to understand. So just to make things easier, or just to make it a standard way of writing, we generally write in annual form, and the interest payments can be sometimes annual, sometimes it can be monthly, sometimes it can be quarterly. So to be able to compare with each and every one, to keep things standard for across all the products, no matter what the frequency is, the companies usually write the annual nominal rate specifying the frequency of the payments. So if the interest rate is 1% per month, we will write 12% per annum payable monthly. If the interest rate is 3% per quarter, we will write 12% per annum payable quarterly. If say it is 6% per half year, we will write 12% per annum payable half yearly. So 1% per month or 3% per quarter, 6% per annum, 6% per half year, all converts to 12% per annum payable in whatever frequency it is. So this way of writing is called nominal rate. This is only for presentation, never to be used in most of the calculation directly. We will only use this directly in the calculations. This will be used very rarely somewhere. But in exam, the questions may be given where the interest rate is expressed in this form. You have to convert it into one of these forms and then use it. So the question will not say it is 1% per month. The question will say the nominal rate of interest is 12% per annum payable monthly. So it should immediately strike to you that it is 1% per month. If the question says the interest rate is 10% per annum payable half yearly, it should immediately strike to you that it is 5% every half year and not the 10% actually. So 5% every half year would convert to 10.25% per annum effective. And if the question says, let's say the interest rate is 15% per half year, 15% per annum payable half yearly. So it should be 7.5% every half year. If the question says the interest rate is 20% per annum payable quarterly, so it should be 5% per quarter. So that is how we should immediately be able to convert your rate of interest from the given nominal rate to the applicable effective rate. So this statement is given, you either convert it to here or you convert to here. Converting from this rate to this rate is pretty just a mental calculation. You don't need to use calculators. From here to here you may require a calculator. So we'll define some notations for this right now, and then we'll see how to convert from one rate to another in a very short span of time, rather very quickly. So let me introduce you to the notations that we can use to write this interest rates. So one of the notation that we use is I, and we write P in the superscript in the brackets. So this IP refers to nominal rate of interest per annum payable, or equivalently we can use the word convertible. Both means one and the same thing, payable or convertible, P times a year. So IP is referred to as the nominal rate, and P here is the frequency of the payment. So if it is per month, your P should be 12. If the frequency is half yearly, your P should be 2. If the frequency is every 3 months, that is every quarter, your P should be 4. If the question says frequency of the payment is, let's say 2 months, every 2 months you get interest payments, so your P should be equal to 6 and so on. So here this interest rate, this particular statement can be written as I 12 instead of P. I write 12 is equal to 12% per annum. This is how I can use this notation over here. Similarly, IP upon P. This is effective rate of interest for pth time period. Effective rate of interest for pth time period. So if I divide this 12% by 12, I'll get this 1%. So for that pth period of the year, that is either of a month or a half year or a quarter, whatever time period it is, if you divide your nominal rate by the frequency, you'll get the effective rate of interest. This can be written as I12 divided by 12, which is 12% upon 12, which gives you 1%, which seems logical. And this simply I is effective rate per annum. Effective rate per annum, effective rate for the pth part of the year, and if a nominal rate. There are three notations. This is effective rate. This I is 12.682503%. So I hope this is very clear to you. Let us look at one more example to understand this in better details. So if I take the interest I is 5% per half year. 5% per half year. So I can write this as, the frequency here is twice in a year. So I can write I 2 upon 2 is 0.05. And 5% every half year means that it is 10% per annum, but nominal I2. The actual rate is not 10%, just the way of presenting it is 10% per annum, payable half yearly. So payable half yearly means frequency is 12. So I can write I2 is 10% and I2 by 2 is 0.05, which is basically 5%. Or this you can write as 0.1, one and the same thing. Now we need to find I. So let's assume that rupees 1 is invested for 1 year. So at time 1, you will have 1 into 1.05 raised to 2. This much money with you. Now 1.05 square is, let's check what is the value. 1.05 square is 1.1025. That means if you invest 1 rupee, you will get 0.1025 rupees extra. That means 10.25% is your I per annum. So this is how you convert I, I2 and I2 by 2. All three rate of interest can be written this way. This is effective rate per annum. This is effective rate for half year, and this is nominal rate for year, convertible half yearly. Never to be used in the calculation. 10%, 5% per half year or 10.25% per annum can be used in the calculation directly. They are the actual rate. Effective rate means actual rate, and nominal rate means just a way of presentation. It is not the real rate of return. So it's just a way of presenting and never to be used directly in the calculation anywhere directly. We'll see what are the formulas later on, which involves sometimes direct use of nominal rates. Otherwise, nominal rates are very rarely used anywhere directly. I hope this example and the previous example makes the concepts of nominal and effective rate of interest very clear. Now let us look at how we can derive a formal formula which can calculate this value rather more quickly than what we have done right now. So the principle of consistency states that if the rate of return is payable per annum, if the rate of return is payable half yearly, if the returns are payable quarterly or monthly, the amount of return that you should have at the end of the year should be same. So if 1 plus I is the accumulation factor for 1 year, accumulation factor for 1 year should be 1 plus I, and accumulation factor if the interest rate is P times a year should be 1 plus IP by P raised to P. You can look at this here. I can write this term as 1 plus I, as I've defined I as this. This is 0.1025. So this is 1 plus 0.1025. And this I can write as 1 plus I2 by 2 whole square into 1. This 1 I can ignore. 1 plus I2 by 2. 5% is I2 by 2 whole square. So the equation that I had written can be written in this way, which looks like this. So this basically logically means that let the interest be payable once in a year, or let the interest be payable in P installments. So if it is half yearly, 1 plus half yearly rate raised to 2. That means that accumulates to 1 year. Or if it is quarterly, 1 plus quarterly rate raised to 4, that which also accumulates to 1 year. If it is monthly, so 1 plus monthly rate raised to 12, which also accumulates to 1 year. So let your accumulation be directly of 1 year through I, or let your accumulation be through any other frequency, more than once in a year, less than once in a year. Your accumulation factor should always be equal. So this statement I can assume to be true, assume or consider true, either through this example or through the concept of principle of consistency. Both gives you the same answer. So this is the relation. So I can write I as 1 plus IP by P raised to P minus 1, or this is one of the important thing to note. I derived it from here, or I can write 1 plus I raised to 1 by P minus 1 is equal to IP by P. I took P over here and subtracted 1, so I get this answer for IP by P, and similarly I can get IP is equal to P into 1 plus I raised to 1 by P minus 1. Multiply this P here, you will get an equation for nominal rate. So it will be very rare that you require nominal value using the effective rate. This kind of question may just be asked to check your calculations. Otherwise, you mostly require either this information or this information. So this is to convert from nominal rate or the effective rate for the pth time period to effective per annum. And this is to convert effective per annum to effective period for the pth time period. So effective to effective or nominal to effective to effective, and nominal from effective. That is how you can interpret these formulas. These are very easy to remember formulas. Just make a note of it. Don't try to memorize it. Just keep a note of it somewhere, one of the formula sheets. Use it. Look at the formula sheet and use it whenever you want to. And eventually you'll see that in certain weeks, maybe in 2 weeks, you'll be able to remember these formulas yourself. You may not have to refer to the book again and again. So sitting and memorizing is not advisable. Keep a note. Refer to the book whenever you want to. Always refer to the formula and solve until you, by default, get used to the formula and it gets memorized automatically. You don't need to take efforts to memorize this, otherwise these are pretty easy formulas to understand. One more example we can see to understand these formulas are, let's say I tell you that interest rate is, let's say 2% per quarter. So I can say that I 4 by 4 is equal to 0.02. Now if I want to find I have a direct formula, 1 plus I4 by 4 raised to 4 minus 1. Now what is this formula actually doing? So forget the formula for the time being. We know that the quarterly rate of interest is 2% and we need yearly rate. So let's assume 1 rupee is invested at 2% accumulated for 4 quarters. So this will give you accumulated value of 1 rupee by the end of the year. And then you subtract that 1 rupee again. This will give you the interest amount for that 1 year, which is actually what we want. This one can be ignored and the rest formula is what you have written above. So even if you know the common sense that 2% is per quarter and you need yearly, so accumulate 1 rupee to 1 year and then subtract 1 rupee again. You'll get your answer. That's how it works. So you can find your answer this way. Let's check what the answer is. So answer is 0.08243216, and you can write I4 is equal to 0.08. I hope that is pretty clear now. So the next topic is nominal and effective rate of discounts. Interest rates, now it is discounts. It works similar, there is no much difference. So now having understood the notations for interest rates, I can feel free to write the notations for discount rates directly. So DP is the nominal rate of discount per annum payable or convertible P times a year. DP upon P is effective discount per annum for effective discount for pth time of a year. So if it is the discount rates are payable suppose monthly, and if you write D12, it is nominal rate of, if monthly discount is 1%, I can write D12 is 12%. 12% per annum payable monthly. And D12 by 12 can be written as 1%. And that is 1% is monthly interest, monthly discount rate. And D is the effective discount per annum. So using all the same logics that we have seen for interest rate, we can say that I discount for one scenario, the discount factor using D being the annual rate here, should be equal to discount factor using the rate of interest, rate of discount, which is for a frequency more than once in a year. So if it is suppose monthly, so 1 minus D12 by 12 raised to 12. So you have to, if your discount rate is per month, you have to discount 12 times. D12 by 12 whole raised to 12, and this should be equal to the discount for 1 year using the annual rate. So discount for 12 months using monthly rate and discount for 1 using annual rate should give you the same answer. Similar discount for 4 quarters using quarterly rate is equal to discount for 1 year, and this is discount for 1 using the annual discount rate. So principle of consistency says that this both should have exactly the same answers. So hence we can write this formula just by the same justification that we gave for interest rates. I've just converted all positive i's to negative d's, and the formula is as it is. So I can derive a formula d is equal to 1 minus dp by p whole raised to p. One of the formula to find d from dp or through dp by p. The other formula is 1 minus d raised to 1 by p is equal to 1 minus dp by p. Therefore, dp upon p is equal to 1 minus d raised to 1 by p. This is to find dp when the effective rates are given, and therefore you can find p is equal to p into 1 minus d raised to 1 by p. This is to find nominal rate when the effective rate is given. I just multiplied this p over here and I got my answer for dp. That is how it works. So I have got conversions from d to dp, dp to d, or from any of the form to dp by p. We have formula for I to ip and ip to I, and from any of the form to ip. So this is all about the nominal and effective discount rate and interest rates. Let us solve a few questions on this to get a better handling or better grasping of how to calculate these values numerically before we move on to the next topic, that is force of interest. So now let us look at few examples of conversions from one rate to another rate. So let me say that I is equal to 0.08. You need to find I2, I4, I12 by 12, D, and D6 and D4 by 4. Everything using I. We can convert well from I to value of D and D6 and D4 by 4 as well. We'll see how to do that right now. I'm sure you must have got a guess by looking at the previous videos if you understood things very correctly. And here things will become pretty much more clear. So we have a formula that I2 is equal to 2 into 1 plus I raised to 1 by 2 minus 1. So I can use this formula to get my answer. 1.08 raised to 0.5 minus 1. So the calculator is here to do the things for you. Go into 1.08. Do not forget to put brackets wherever they are necessary, otherwise your answers will go wrong. So answer is 0.07846096. I did not do any kind of step-by-step calculation. I just wrote the whole thing in the calculator once and I got my answers. You should do this to avoid any kind of rounding of errors. Now I4 should be equal to 4 into 1 plus I raised to 1 by 4 minus 1, which is 4 into 1.08 raised to 1 by 4 minus 1, which should give me the answer is 0.07776062. It is 1.8, I just rounded up to 2. Then we need to find I12 by 12. I12 by 12 is 1 plus I raised to 1 by 12 minus 1. Now this is very intuitive again. Let us say first 1 plus I. 1 plus I is the accumulation factor for 1 year. If I make it raised to 1 by 12, this should become accumulation factor for 1 month, because n 1 by 12 means accumulation for 1 month. Assuming 1 rupee was accumulated, subtract 1 rupee here again. So you get 1 rupees accumulated value minus 1. So the amount that is left is the interest earned over 1 month, which is I12 by 12 actually. So this formula again should be very intuitive, and you don't need to actually remember any kind of memorize any kind of the formula for this. This is exactly what we wrote in the previous video, but this is something you can remember yourself without referring to anything else. Just a common. If you want effective for 1 month, make it 1 month. If you want effective for 2 months, make it 2 months. If you want effective for 3 months, make it 3 months. If you want effective for 6 months, make it 6 months. That is how it should work. So let's see what the answer is. 1.08 raised to 1 by 12 minus 1. And the answer comes out to be 0.0064343. This is my answer for effective rate of interest per month. Now I can find D. D is equal to I upon 1 plus I, which is 0.08 upon 1.08, which is 0.074074074. This is my discount rate. Once I found the discount rate, I can find D6. D6, I can write it as 6 into 1 minus D raised to 1 by 6, or I can also write this as 6 into 1 minus 1 plus I raised to minus 1 by 6. If you remember, we had stated that 1 minus D is equal to 1 plus I raised to minus 1. This was discussed in the where we discussed the relationship of I and D. We had written this equation very clearly. If you do not remember, just go through it once. So I replaced 1 minus D by 1 plus I raised to minus 1. Both are actually the discount factors. Let me see what the answer is. You can use either of the formulas. You can use either this D over instead of this D in place of this D, or you can use I directly. I would prefer to use I directly because I want to avoid any kind of rounding of errors. If you have rounded off this D to 4 or 6 decimal points, you'll get a different answer slightly, which is also acceptable, but the error should not be much. So I personally want to avoid errors completely. So I will directly use the given information I in the equation. So my answer is 0.076469556. Yeah, that's correct. And then I have lastly D4 by 4, which is equal to 1 minus D raised to 1 by 4 minus 1, if I am not wrong, which can also be written as 1 plus, it is 1 minus D raised to 1 by 4. That's the answer. Or I can write this as 1 minus 1 plus I raised to minus 1 by 4. That's what I'm going to do. I've just replaced again 1 minus D by 1 plus I raised to minus 1. And the answer comes out to be 0.019053. So this is how we convert from any rate to any other rate. I think it was pretty smooth and not very difficult to understand. So having understood this, now we can move on to the further topics. Okay, so now let's move on to the last topic of the chapter, that is called as force of interest. Force of interest is nothing but the nominal rate of interest. I can define this as nominal rate of interest per annum payable, or rather convertible, continuously. Nominal rate of interest, or I would say discount, per annum payable or convertible continuously. I can also use the word weekly, or I can use the word daily. So when we say DP or IP, when we use these terms IP or DP, we say the interest is being paid more than once in a year. But here the P is always the countable number of times. So be it months, be it quarters, be it half years, you can count this on your fingers. The numbers are very less. But what if I tell you that I'll pay you interest 100 times in 1 second? Or what if I tell you if I'll pay you interest 500 times in 1 second? Or what if I tell you I'll pay you interest 1000 times in 1 second? This sounds a little bit impractical, but that is what the actual definition of continuous is, and it is one of the very important topic in this chapter and rather in the subject to understand. Because generally it happens, if you think of any kind of a business, the money is continuously flowing into the company. So think of Paytm, think of Flipkart, think of Amazon. Someone or the other is buying something from their website every second from one of the corner of the world. So money is coming in continuously, and that money is going to the bank. So bank will definitely pay them interest on the same basis. So there is a different amount for different time period. So in real life, in many places, you can think of earning continuous rates. If you put your money in the stock market, you may earn some returns every second. So considering the rate of returns earned per second for a time period which is very small is very important. So continuous by default means more than once in a second, more than 10 times in a second, more than 20 times, infinitesimally as small as you can imagine. But even if the question says the interest payable daily or weekly, we will assume it to be continuous, because the difference is not much. So for daily or weekly, we'll assume continuous, but by default, the definition is for continuous. So as I say, it is the nominal rate. It is simply IP, where P is tending toward infinity. When P is tending toward infinity, IP is called as the force of interest, and instead of IP, we denote it by a notation called delta. So delta is a notation that we are going to use for force of interest, and it is nothing but IP where P is infinite. The frequency is so large that you cannot count it on your fingers. Also, if I say DP, it still means the same thing. Now throughout the chapter, we have been assuming that I and D have a different value. So when let's suppose I say D12 or I12. I12 means interest payable at the end of every month. D12 is interest payable at the start of every month. When I say I2 and D2, it is start of every 6 months or at the end of every 6 months. So even if it is I12 monthly, I12 or D12, the interest payable at the end of the month and interest payable at the start of the month has got a time gap of 1 month. So definitely there is a difference in the payment. But when I say the interest is being paid every second, so interest is paid at the start of every second will refer to D infinity, and interest is being paid at the end of every second is being referred to as I infinity. So when I say interest is paid at the start and at the end of every second, the difference is less than a second. So if the difference of the payment is just less than 1 second, how can there be a difference at all? So the interest that you're going to be paid, be it at the start of 1 second or be it at the end of 1 second, is going to be same. So as I can say that as P tends to infinity, DP tends to become IP, or IP tends to DP. I can write both. So both of this are exactly basically one and the same statement. For if P is tending to infinity, IP and DP becomes equal, and both are referred to as delta. So that is one point for introducing the notation itself. Now accumulation factor. If I want to accumulate using IP, I used to do 1 plus IP by P, the whole thing raised to P. 1 plus IP by P, the whole thing raised to P gives me accumulation factor using IP. Now when I say limit P tends to infinity, what does it become? So if you know, if you do not know, it is fine, but if you know, it is good. Limit m tends to infinity, 1 plus x upon m, the whole thing raised to m is e raised to x. This is the well-known result of an exponential function. If you do not know, many of you must have not gone through this result. So if you do not know, it is okay. You can just keep in mind this result henceforth. So this is one of the result to define the exponential function. And this looks exactly similar to this. Just instead of x, we have ip over here. This m is p, which tends toward infinity. So this should become e limit p tends to infinity ip, which can further be written as e raised to delta. So if you want to accumulate using force of interest, this is the formula that you're supposed to use. Also, limit p tends to infinity, I am writing this for discount factor. 1 minus dp by p raised to p becomes e raised to minus limit p tends to infinity dp, which can be written as e raised to minus infinity, and which are inverse of each other, which is also true for this case. We had mentioned at the start of the video that accumulation factors are also inverse of discount factors. So this is a accumulation, this is a discount factor, which are inverse. This positive x, hence here we had positive, here it is negative, so I just put negative sign and I get negative in the power. So these are the accumulation factors and discount factor that you can use to solve questions involving force of interest. So not very difficult again, it's pretty easy. So you have I is the interest payable once at the end of the year. Then you have IP, interest being paid more than once in a year or less than once in a year. So frequency is not equal to 1. For frequency anything not equal to 1, we use IP, where P should be equal to a number which is countable on your fingers kind of. So it should be small. And if P becomes infinity, we use delta instead of it. And we have D. D is the interest payable once at the start of the year. If interest is payable more than once in a year or less than once in a year, we use DP. If again interest is payable at the start of time unit but infinite number of times, we use delta. So I, IP, D, DP, and force of interest. These are the 5 important types of interest rates you need to remember. These are not actually types of interest, all are compound interest only, but we have different names or different notations defined based on the frequency by which the interest is being credited to your account. That is how it works. So make a note of these things. Let us now solve a few questions on this. So now we will try to find out some relations between the force of interest, discount rate, interest rates, IP, that is nominal rate of interest and nominal rate of discount, and do some more complicated kind of questions which are not actually complicated but look complicated at once when you see it for the first time. So let's see. We had written 1 plus I was equal to 1 minus D raised to minus 1. Then we found another relation that 1 plus I is equal to 1 plus IP by P whole thing raised to P. Then we said 1 minus D is equal to 1 minus dP by P whole raised to P. Then we also said that when P tends to infinity, 1 plus IP by P whole raised to P becomes e raised to delta. Now principle of consistency says that it doesn't matter how the interest is being paid. Interest is being paid at the end of the year using I, or interest is being paid at the end of regular intervals using IP, or whether interest is being paid at the start of the year using D, or whether interest is being paid at the start of regular intervals using DP, or whether interest is being paid continuously throughout the year using delta. The amount that you hold at the end of the time unit in your account should remain same in all the cases. That means the accumulation factor using all the kinds of interest, I, D, DP, IP or delta, using all these kinds of interest, the accumulation factor that you have at the end of the year should be equal. So accumulation factor using I is this, which was by default equal to 1 plus ib by p raised to p that we had written. I can say that this is equal to 1 minus d raised to minus 1. And hence I can say that this is also equal to 1 minus dp by p whole raised to minus p, which is also equal to e raised to delta. So these are the accumulation factors using different rate of interest, and all of them are said to be equal, or all of them should be equal. That is the rule number 1. Or you can say that discount factors using all of these. 1 plus I raised to minus 1 is discount factor using I, or 1 plus I p by p whole raised to minus p, or 1 minus d, or 1 minus dp by p whole raised to minus p should be equal to whole raised to p should be equal to e raised to minus delta. So once you have this master formula with you, you can convert from any kind of interest rate to any other kind of interest rate. Want to convert from I to dp, dp to delta, delta to d, whatever conversion you want. Either you keep this in mind, the accumulation factors of all of them are equal, or you keep this in mind, the discount factors of all of them are equal. Once you have one of these two equations in mind, converting from one rate of interest to another rate of interest should never be a problem. So this is a very simple, straightforward, easy to understand relationship of all of them. We can derive individual relationships using this. And using this, I'll derive some relationship which are more frequently used. I can see e raised to delta is equal to 1 plus I. Therefore, I can write I is equal to e raised to delta minus 1. This is how you find I when delta is given. Or I can say log of 1 plus I should be equal to delta. Taking log of both the sides, I get this result. How to find delta when I is given. Second thing, e raised to minus delta is equal to 1 minus d. Therefore, minus delta is equal to log of 1 minus d. Therefore, delta is equal to minus log of 1 minus d. This is how you find delta when d is given to you. Simply you can write d is equal to 1 minus e raised to minus delta. How to find d when delta is given. So these relationships are more frequently used. This you should definitely keep in mind. But other relationships can be derived spontaneously whenever the question comes up in the exam, or whenever the situation arises to derive a relationship. So keep this equation in mind along with these formulas, which are obviously the simplification of the above equation, so that you never face problem in converting from one rate of interest to another rate of interest at any point of time in any kind of exam question. So these are the relations which you should definitely know. Keep a note of them and practice them. Use them whenever you want while solving. Refer to them once, and automatically with time you'll get used to it. You don't need to spend your energies in memorizing these formulas. This should be natural to you that you know these formulas by solving, not by memorizing. Let us solve a few questions for considering force of interest. So let's say rupees 200 is invested for 5 years and delta is given as 0.07. Now you have to find the accumulated value at time 5. So accumulated value is equal to 200 e raised to delta into 5. This is how we write the equation. So this is 200 into e raised to 0.07 into 5, and the answer can be directly calculated from the calculator. We have the exponential function in the calculator itself. So answer comes out to be 283.8135. Simple. Now next, let's say rupees 500 is due at time 6. Delta is 0.09. Find present value. So present value is 500 e raised to delta into 6, and this should be negative because you're finding present value. So 500 e raised to minus 0.09 into 6. Let's see what is the answer. 500 into e raised to 0.09 into 6, and that should be negative. So answer is 291.374126. So this is how you find present values and accumulated values using force of interest. So this is all about the simple cases of force of interest. The force of interest can sometimes be given in a bit complicated way. So force of interest sometimes can be given to you as a function of time. Function of time means it changes its value as the time changes. So now we are going to consider some cases where force of interest is considered as a function of time. Let us have a look at it. Let us understand force of interest when it is given as a function of time. So force of interest as function of time. We would denote this as delta of t, that is function of time, delta t. This is basically a function of time. Let's say, for example, my delta t is given as 0.08 plus 0.01 t, where t can take any value between 0 to 5. Now, how do you interpret this kind of a function? So force of interest is nothing but the nominal rate of interest. You're earning some rate of return, and at time 0, this t becomes 0, your rate of return is 8%, 0.08. At time 5, this t is 5, and your rate of return becomes 0.08 plus 0.05 when t is 5, and this becomes 13%. So your rate of return starts from 8% and increases gradually to become 13%, and the function by which it increases is linear. So from 8% to 13%, it increases linearly throughout the time period. So every day you are getting some return at the increased rate. It is at time 0.5 it is 8.5%, at time 1 it is 9%, at time 1.2 it is 9.2%, at time 1.7 it is 9.7%, and so on. So every day, whenever you're getting returns, your returns are being added to you or your account at the increased rate. This is how we interpret this. So your rate of returns are increasing. Now, how do you deal with such kind of a function? We need to find accumulation factor first. So when delta was constant, we did e raised to delta into n. Now the delta is not constant, so delta is a function, so you cannot simply do delta into n. It would not give you a good answer. So when delta is a function of time, what you have to do is e raised to integration from 0 to n delta t dt. We'll see what is the logic of this right now. So here you integrate the function, the force of interest given, from time 0, that is the point where you're investing, to the time n where you want to find the accumulated value. This is accumulation factor from 0, n. Similarly, we can find discount factor, which is inverse of accumulation factor, as 0 to n delta t dt. When we have seen this, that discount factors are always inverse of the accumulation factors. So once you know this is accumulation factor, this is the inverse of it is a discount factor. So let us keep this in mind, and we'll see how what may be the possible reason behind this right now. So what is basically integration? So when you integrate something, let's say I integrate x from 1 to 5 or from 0 to 5, what really happens is this integration splits your function x into small parts. It tries to find out what are the values that x can take in the range that you have specified. So it can take value 0, it can take value 0.1, it can take value 0.7, it can take value 0.00008. Any number, any smallest possible number, infinitesimally small number that you can imagine between 0 to 5. Integration identifies all such possible points in this range and adds them all together. So integration is nothing but adding up a variable over a continuous range. Integration adds up your variable over a continuous range. When you do summation of x from 0 to 5, summation adds up your function over a discrete range. Integration adds up a function over continuous range. So now when you integrate, you are basically adding up. So let's say if my delta was 0.08, it was just a constant, and I do e raised to integration from 0 to 5, 0.08 dt. I would get my answer as e raised to 0.08 t from 0 to 5, which is e raised to 0.08 into 5. This is what answer I got. Since my delta was constant, my accumulation factor was anyways e raised to delta into n, which is exactly what I got by even by integrating. So even if it is constant and you integrate, there is no issue. But when it is a function, you cannot simply write e raised to delta into n, then it becomes mandatory to add. So basically your 0.08 gets added 5 times when you multiply it by 5. Here it is a function, so when you want to add up a function, you want to add up all the possible values. Now let's understand, the other way to understand it may be, when I write 1 plus I raised to 5, I can write it as 1 plus I raised to 2 into 1 plus I raised to 2 into 1 plus I. This is one of the way of writing. Or I can write 1 plus I raised to 0.5 into 1 plus I raised to 0.5 and so on until it becomes 5. Or I can make it 1 plus I raised to 0.001 into 1 plus I raised to 0.001 and so on until I get the total power to be equal to 5. So 1 plus I raised to 5 can be split into this way. Now since here when I write 1 plus I raised to 5 and I assume that I is constant throughout the year, I can simply I can simply do 1 plus I raised to 5, I don't need to split it if my interest rates are same. But if I tell you that interest rate changes at every 0.5 time period, you'll have to mandatorily do this. You'll have to break a function and then multiply them together. So power gets added for all of them. And if I say that your interest rate is changing every 2 years, so 2 and then 1 year, you have to split it this way. So here when I'm integrating, when I'm doing this, considering this force of interest as a function of time, my function is changing at every minute. So e raised to delta n, what we write as e raised to delta, let's say for 5 years, should not be done like this. It should be done like this: e raised to delta into 0.00001 for the smallest possible time. This much time, what is delta? Then again delta into 0.001, possibly something like this. So you have to count the interest rate that is being earned in each and every second. So e raised to delta into n is basically this accumulation factor for n years. When you do e raised to delta into 0.1, it becomes accumulation factor of 0.1 years. So you have to identify accumulation factor of an infinitesimally small time period and multiply them together. So basically when you multiply e raised to something into e raised to something into e raised to something, the power adds up. When the power adds up and when it is continuous range, a simplified version of it can be written as e raised to integration of 0 to n delta t dt. I hope that makes a lot of sense to you. So integrating basically just make sure that each and every minute or each and every second or each and every point in the given range is taken into account and taken care of. And integration is necessary because the function is changing with time. You cannot simply write e raised to delta into n. So this is the accumulation factor and discount factor whenever the function is given. Now let us try to understand how to deal with it whenever the question asks you about it. So I'll write it here. So let's say you want to accumulate rupees 100 to time 5. So we'll do 100 e raised to integration from 0 to 5, 0.08 plus 0.01 t dt, which becomes 100 e raised to 0.08 t plus 0.01 t square by 2 from 0 to 5. 100 e raised to 0.08 into 5 plus 0.01 into 5 square by 2 whole thing minus 0. So further answer can be evaluated using the calculator. So 100 into e raised to 0.08 into 5 plus 0.01 into 5 square by 2, And the answer is 169.04588. So here I assume the investment was made at time 0 and I want to accumulate this to time 5. Let's say if I want to find present value of rupees 1000 due at time 6. So 1000 e raised to minus 0 to 6. You want to bring the value down to time 0 from time 6. 0.08 plus 0.01 t dt. Solving the same way, it becomes 1000 e raised to minus 0.08 into 6 plus 0.01 into 6 square by 2 minus 0. So let's see what the answer is. I hope you understood. I just used the same thing. Here it was 5. So here we got 5. Now we have 6. So I took 6 here. The other part is by default 0 and there is a negative sign. So 1000 into e raised to minus 0.08 into 6 plus 0.01 into 6 square by 2. And the answer is 516.85133 rupees. So this is how you deal with the force of interest when the force of interest is given as a function of time. So pretty easy. You just need to integrate whenever it is as a function, and when it is not a function, you just take the value as it is and multiply it by n. That would give you answer pretty easily. So that is it in the chapter. Let us watch the another video, the next video, which involves a lot of sums in the chapter. The chapter ends here. We need to introduce a few complications, the questions that will be introduced in the next video. Before we wind up the chapter, let me introduce to a new interesting term. So a new term which is used for discounting, and the term is V. V is discount factor for 1 year. V is a discount factor for 1 year, or if I write V raised to n, it becomes discount factor for n years. So we wrote V raised to V and bracket n as a discount factor. This is just an alternative way of writing. V raised to n can be written as Vn. Both are one and the same thing. But while solving sums, we'll be using this term more frequently. I would say every time, not just more frequently. Every time we'll be using this term instead of this term. So for example, if I want to write present value of rupees 100 due at time 10. So this is written as 100 V raised to 10, which means 100 rupees is being discounted for 10 years. Now once you write this, then you look at what further information is given. If the question gives an information of I, you then write this as 100 into 1 plus I raised to minus 10. So discount factor for I is 1 plus I raised to minus n. Or you can write it as 100 into 1 minus d raised to 10. Or you can write this as 100 into e raised to minus delta into 10. So discount factor of every kind of interest rate is being denoted by V basically. So V raised to n, or I would just write V is equal to 1 plus I raised to minus 1, or it is equal to 1 minus d, or it is equal to e raised to minus delta, or it is equal to 1 plus ip by p raised to minus p, or it is equal to 1 minus dp by p whole thing raised to p. So V can be a replacement of a discount factor of every kind of interest rate. When it is V raised to n, it becomes 1 plus I raised to minus n, or 1 minus d whole thing raised to n, or e raised to minus delta n, or 1 plus ip by p whole thing raised to p into n, or 1 minus dp by p whole thing raised to p into n. Here it is negative. So V is a discount factor for n. We can also write V raised to n as integration of 0 to a raised to minus integration of 0 to n delta t dt. This can also be written as V raised to n. So discount factor of any time, not just the interest rates when they are constant, even when it is a function of time, you can use V raised to n as its discount factor notation. So finally the chapter ends here, and now the next video that you will be watching will be a video that is meant just to solve the questions. If the force of interest part if you found the force of interest part heavy because of the integration involvement, I would advise you to revise the integration basics from your class 12 book or the ACET books of the Institute of Actuaries of India or any other institute that will help you in revising the basics, and then you solve it. So integration involved, at least in the initial part of the subject, is not very complicated. It is basic, quite simple. And later on, in the final few chapters, you might find integration which involves a little bit more complex integrals. So you will get used to it eventually when you start practicing. So to start with the initial part, CM1 of CM1, you need to go through just the basics, very few basics of your class 12 integration, and then watch the video of practice sums. And the practice sums will be discussed on the assignment that is being supplied to you. So have a look at the assignment. You can first try to solve it yourself. I know what are the questions you might find complicated, and I'll be making a video only to solve those questions. And if you have solved it before, it will be good for you. If you have not solved it before, you can watch the videos and solve it, whichever way you find more comfortable. Thank you so much.